Okay, so we are recording. So if you talk, you're gonna be recorded, just so you know. Okay. So in chapter 10, it's a trigonometry unit. So trigonometry is like the study of triangles. And specifically, we're going to focus primarily on right triangles. So we're going to be dealing with trigonometry topics involving usually right triangles, but we have a little bit of preliminary work to do before we get into the right triangles. Make sense? Okay. So, we've been working on geometry stuff, for chapters 8, 9, and now 10. So it's all kind of connected to this idea of geometric stuff. Looking at it from a practical application kind of perspective. Okay. So converting angle units. In most practical work, angles are measured in degrees and fractions of a degree. Smaller units have been defined as follows. So essentially what's happening is like when we're measuring an angle, if you think about like a full revolution, like a full circle, let's say if you're starting here with this line and you do a full revolution, that's 360 degrees, okay? So 1 degree is 1/360th of a full revolution, okay? So that's sort of the definition of a degree. And so a degree is going to be really small, right? We used like protractors earlier and so on, so you know what a degree is, okay? Well, 60 minutes equals 1 degree, or we can abbreviate that. Minutes is just like an apostrophe, okay? Or we call that a prime, a minute symbol. So 60 minutes equals 1 degree, and 60 seconds equals 1 minute. So, and the abbreviation for seconds is like a quotation mark there. So 60 minutes, 60 seconds, it would be denoted that way. So again, that means that 1 minute is 1/60th of a degree, and then 1 second is 1/60th of a minute. So 1 second is 1/300, but it's 1/3600th of a degree. Okay, does that make sense? Now those are so fine that we're not going to usually measure things to the nearest minute. We could, or the nearest second, hardly ever in real practical work, but we could. Instead, we would normally use like fractions of degrees. So we might say 74.5 degrees or something like that, okay? For most technical purposes, angles can be rounded to the nearest minute. In the trades, angles are usually rounded to the nearest degree. Sometimes in your work, you will need to convert an angle measure in decimal degrees to its equivalent measure in degrees and minutes, okay? So for example 1, we're just going to do a conversion between like degrees and minutes and seconds, or really we're going to be doing like parts of a degree, so like a fraction of a degree into maybe minutes and seconds, okay? So convert each angle measure to degrees and minutes, round to the nearest minute, okay? So what we have here is 41 2/3 of a degree. So it's going to be 41 degrees and so many minutes, okay? And so, so again, we're supposed to round to the nearest minute. So it's really the 2/3 of a degree that we need to convert, okay? And we really do this like any other unit conversion. So if I have 2/3 of a degree, okay, if I will multiply that by the fact that there are 60 minutes in 1 degree, that will cancel out the degrees and leave me minutes. Does that make sense? So really all I'm going to do is take 2/3 of 60. Well, 2/3 of 60 is 40. I said 40 and typed that in my calculator. 2/3 of 60 is 40. So that is 40 minutes. So 41 2/3 degrees would be the same as 40 degrees and 40 41 degrees in 40 minutes, I should say. Does that make sense? Likewise, if we have 74.23 degrees, well, that's going to be 74 degrees and some odd minutes. And so if we want to change the 0.23 degrees into minutes, we're really just going to multiply by 60 over 1 degree. So the degrees will cancel and we'll really just multiply them by 60. So 0.23 times 60 is 13.8 minutes. And our directions say round to the nearest minute. So that would be about 14 minutes. So 74.23 degrees would be the same as 74 degrees and 14 minutes approximately. Piece of cake? Okay. Example 2. Convert each angle measure to a decimal degrees, round to the nearest hundredth. So we have 68 degrees and 15 minutes. And so we're going to go back the other way. We're going to change the 15 minutes into a decimal degree. So this is going to equal 68 point something degrees. So I have the 15 minutes. And so I know that, that it takes 60 minutes to be 1 degree. So that will cancel out the minutes and give me degrees. So if I take 15 divided by 60, that's 0.25. So 15 minutes is the same as a fourth of a degree, or 0.25 degrees. So it's going to be 68.25 degrees. Make sense? Again, in most practical work, you're never going to be more accurate, more precise than the nearest minute. And nowadays, with like the electronics and so on, usually instead of using minutes, we use decimal degrees. Okay. So same idea, 129 degrees and 16 minutes. Well, if I convert the 16 minutes to degrees, 1 degree is 60 minutes. So really, I'm going to divide 16 by 60. And so that is 0.26666 repeating. And we're supposed to round to the nearest hundredth. So that would be 0.27 degrees. So 129 degrees and 16 minutes is going to be approximately 129.27 degrees. Does that make sense? Okay. So not too horrible. Okay. Now, something else you might see, again, in most practical work, angles will be measured in degrees and then possibly in minutes and seconds. Okay. There is another measure of angles called radian measure. Okay. And so you could encounter radian measure as well, depending on your particular field. Okay. So in some scientific and technical work, angles are measured or described in an angle unit called the radian. 1 radian is the angle at the center of a circle that corresponds to an arc exactly 1 radius in length. So that's kind of a weird definition, but that's the definition. Okay. So if you look at this angle right here, so this angle A here in this figure, okay, so the radius of the circle here is R. So if I measure that same distance R up around the circle, you visualize that, then the angle that's formed here is 1 radian. And it doesn't matter how big the circle is, okay? So if I have a bigger circle, the radius is going to be bigger. And so I'm going to measure up the circle, the same distance as the radius. But even if I've got the bigger circle, the angle is going to be like, if this is if the radius is this long, then this is going to be the radius here. And so it's going to be the same angle, 1 radian. Okay, makes sense? Now remember, 1 full revolution is 360 degrees. Okay, and we know how to find the like the circumference of a circle is 2 pi times the radius. So 2 pi times the radius is equal to 360 degrees. Okay, so I mean, to make a long story short, if that is equal to 360 degrees, then the radius would equal to 360 degrees over 2 pi. And if you divide by 2, that would be 180 degrees over pi. Does that make sense? Okay. So if you had a full revolution, that's 360 degrees, and that's 2 pi r radians. And so 1 radian is equal to 180 degrees over pi. And that's what I'm saying here. Okay. So basically the angle right here, if you think about what pi is 3.14159. So if I took 180 and divide by 3.14159, that's about 57.295 degrees, okay, or about 57.30 degrees, okay? So this angle right here, where the radius is, again, the arc length right there, that is about 57.3 degrees. So 1 radian, again, is 180 degrees over pi, okay? Or in other words, it's about 57.296 degrees. Does that make sense? Okay. So that's like a conversion fact that we would be able to use to convert between radians and degrees. Okay. So to convert angle measurements between degrees of radians, which we might abbreviate RAD for radians, use the following formulas. So if we have degrees and we want to convert to radians, then the radians will equal the number of degrees times pi over 180. Does that make sense? Okay. Sorry about that. Oh, okay, never mind. And if we have radians and we want to convert to degrees, we'll take the number of radians times 180 over pi. So essentially, we're doing the same kind of thing. I like to think of it as this, okay? So pi radians is equal to 180 degrees, okay? So what I'm really doing is making a conversion fact. If I have degrees, so I'm going to have degrees here, right? If I multiply by pi radians over 180 degrees, the degrees will cancel, leaving me radians. Okay, you follow me? And vice versa, if I have radians, then if I multiply by 180 over pi radians, the radians will cancel, and you'll be left with degrees. Okay? So again, it just depends on what field you're in, whether you'll actually ever use radians, but they actually come in handy for other things that we'll see as we go along here as well, okay? So write each angle measure in radians and round to the nearest hundredth. So if we have 145 degrees, or not 145 degrees, just 45 degrees, and we want to convert that to radians. So again, I'm just going to use my conversion fact. I have pi radians over 180 degrees. And so that's going to cancel. And we're supposed to round to the nearest hundredth. So I'm going to take 45 times 3.14159 divided by 180. And so that is about 0.79. Okay. So if I round to the hundredths, That's going to be approximately 0.79 radians. Now remember, 1 radian was around 57.3 degrees. Okay, so 45 degrees is a little less than 1 radian. Make sense? Likewise, if I have 186.4 degrees, and I'm going to convert that to radians, so that would be pi radians over 180 degrees. So 186.4 times 3.14159 divided by 180. So that is about 3.25 radians. Any questions about that? Okay. Example 4 is just going the other way. If we have 1.2 radians, how many degrees is that? If we have 129 degrees and 60 minutes, how many radians would that be? Okay. I just realized in my notes here, I have that messed up. Okay. My directions are saying to write the answer in degrees. Well, I have the degrees there. So on part B, this one we're going to change to radians. Does that make sense? So this is more like the previous example where we're going to be converting it. The difference is that we have degrees in minutes here as opposed to the other. And again, we're going to round to the hundredths in this case. So if I have 1.2 radians, again, I'm going to convert to degrees. So 180 degrees over pi radians, that's going to cancel out radians and give me degrees. Okay. So 1.2 times 180 divided by 3.14159. So that's going to be about 68.75 degrees. Make sense? And again, this is the same idea, but again, I goofed up here. I should have had this up like as part C or something up here, okay? But if I have 129 degrees and 16 minutes, what I was going for is, in order to convert this into radians, I'm going to have to, first of all, convert the minutes into like a decimal degree, okay? So like the 16 minutes, we know that there's 60 minutes in 1 degree. So I'm going to take 16 divided by 60. And so that is 0.266 repeating. We actually did that earlier. Okay. We actually did that problem right here. Okay. So that's really 129.27 degrees. Okay. So if I have 129.27 degrees, and if I want to convert that to radians, then I'm going to multiply by pi radians over 180 degrees. Now that really, when I converted the 16 degrees to minutes, that was really 0.26666 repeating. And I'm going to go ahead and carry that out so that I don't have a rounding error. Okay, so instead of saying 0.27, I'm carrying out the 6 a few times, times 3.14159 divided by 180. So that would be about 2.26 radians. Okay. To be totally honest, what I think I did there, I cut and pasted the AB and then I forgot to edit that. Okay. So that should have been a radians that I was converting to degrees. okay? But it's still not a bad example, because if you're converting from degrees and minutes to radians, you really need to get rid of the minutes first so that you can use the pi over 180 business, okay? Piece of cake? Okay. So you'll have homework questions like that. You know, what have we done so far? We've converted between degrees and minutes, right? We've converted now between degrees and radians, okay? Now, what good are radians? Well, here's one application of radians. The wedge-shaped portion of a circle is called a sector. So like a piece of pie is a sector of a circle, okay? Both its area and the length of arc S can be expressed most directly using radian measure, okay? So if I have an angle here, let's say, and I want to know what is the length of the arc that is bound by this angle, then I can do that by using radian measure. And I can also find the area of that wedge, of that sector, by using radians. And so we have these formulas, okay? So the arc length. So the arc length S is equal to the radius times the angle, where the angle is in radians. Does that make sense? Okay. So whatever that length is, I can find it if I know the angle and the measure of the radius. The area of the sector is 1/2 times the radius squared times the angle in radians. Does that make sense? So again, it's kind of like pi r square, you know, that we used before, except that's going to be converted. And for it's the proportion of the circle that it's taking up, which is again going to be the angle in radians. Note, the sector formula will not work unless the angle A is in radians. So, you know, if you have the angle in degrees, you're going to have to convert the angle to radians in order to be able to use these two formulas. Okay, so that's my biggest caution for you. Okay. So for the sector with central angle 80 degrees and radius 0.25 feet, calculate A, the arc length of the sector, B, the area of the sector. So I got a figure here. So we got this angle here that's 80 degrees. So I want to know two things, right? I want to know what's the length of this arc. So like from here to here, how long is that? Okay. And then the second thing I want to know is what's the area of that sector? What's the area of that piece of pie? Okay. So my angle's in degrees. So I'm going to have to convert my angle to radians to be able to use these formulas. Okay. So the arc length S, if I call that S, is equal to the radius times the angle in radians. Okay. So my radius is 25 feet. Okay. And then I'm going to multiply that by my angle. Now my angle is 80 degrees, but I can't have it in degrees. I got to have it in radians. So I'm going to take the 80 times the pi over 180, so that that'll be in radians, and then multiply by the 25. Okay. So I'm going to just kind of do that all at once here. So 25 times 80 times 3.14159 divided by 180. And by the way, that's going to cancel out the degrees. Okay. And so I end up with 34.91 if I round to the hundredths. I didn't say on here where to round to, but I'll round to the hundredths. Okay. Actually, I probably should just round to the 9 because that only has 3 significant digits. The 25.0 has 3 significant digits. So my answer will only be accurate to 3 significant digits. Does that make sense? So that would be 34.9 feet. Does that make good sense to you? Okay. So again, that would be the length of that arc right there. Okay, so just under 35 feet. The area of the sector, well, the area is going to be 1/2 times the radius squared times the angle in radians. So that's going to be 1/2 times 25.0 squared times the 80 degrees times pi over 180 degrees. So 1/2 times 25.0 squared times 80 times 3.14159 divided by 180. And so that is about, let me make sure I type that in right. 80 times. I don't see any mistakes. So that's about 436.33 square feet. I think I'll just round to the 10th place. Square feet. The units are square because it's area, okay? Or really it's 25 feet here that's being squared, and 25 feet squared is going to be square feet, right? Makes sense? The interesting thing and the nice thing about radians is like when I was doing this right here, I wrote radians like it's a unit, but radians really kind of aren't a unit. Okay, so like when I divide out here, I'm left with whatever that is, radians. But when I take the radians times the square feet, it's just square feet. Radians really aren't a unit. Okay, does that make sense? So you don't end up with like square feet radians or anything like that. Okay. Still good? Okay. So that's one application where we'll see radians, is if you're trying to find an arc length or if you're trying to find the area of a sector of a circle. Okay. Radian units are also used in science and technology to describe the rotation of an object. When an object moves along a straight line for a distance d in time t, its average linear speed v is defined as v equals d divided by t. So that's like our definition for linear speed. So again, what's v? That's the average linear speed, okay? So v really is there for velocity, and velocity is really the same idea as speed. The only real difference between velocity and speed, well, technically the speed is the absolute value of velocity, okay? So velocity could technically be negative. It's not in most practical applications, but like if something's traveling like downward in a negative direction, we would say it has a negative velocity. If something's heading upward in a positive direction, we would say it has a positive velocity. With speed, we don't worry about direction. We just say what the speed is. Does that make sense? Okay. So anyway, so technically V is for velocity as opposed to speed, but speed's essentially the same thing in most practical applications. Okay. And so once again, D is the distance and T is the time. So we're going to end up with something like miles per hour or feet per second or something like that. It's going to be a measure of distance over a measure of time. Okay. So if a bicycle travels 24 miles in 1.5 hours, find its average linear speed. Okay, well, its average linear speed is going to equal the distance divided by the time. Well, if we go 24 miles, excuse me, in 1.5 hours, then to find the linear speed, all I got to do is divide. So 24 divided by 1.5, that would be 16 miles per hour. Or sometimes we say MPH for miles per hour. Okay. So if you'll remember back when we did like ratios and proportions, this is like a ratio and proportion. It's called a rate. So the difference between like a ratio and a rate generally is that in a ratio, you would have the same units like on the top and the bottom, so the units go away. In a rate, you have different units, so you have to kind of keep them. Okay, so you're comparing one kind of unit to another kind of unit, like in this case, distance units to time units. Okay. So nothing to that, right? You already knew how to do that, I think. Okay. When an object moves along a circular arc for a distance s in time t, it goes through an angle A in radians, and its average angular speed W is defined as W equals A over T. Okay, so that's going to be our definition for angular speed. Okay, so essentially what we're doing is, if you visualize, if I pull back up, okay, so like if say this is like the Earth, right? And you got a car traveling along, you know, the edge of the Earth, right? So if it's going to be traveling this distance, then there's an angle here that's changing, so to speak. Okay, so the angular speed would be how much the angle is changing over time, as opposed to what the distance is over time. Does that make sense? Or suppose like this is a tire, right? So you got the wheel with the tire on it. So if the tire rotates this much in a unit of time, then how much did the angle change in the unit of time? That's the angular speed. Okay. Now, usually we measure angular speed in things like RPMs, revolutions per minute. So that would be like a pulley or something like that, a gear or something that's rotating. Does that make sense? Okay. And so we get their angular speed in revolutions per minute. Okay. But we don't have to. Okay. Note, the angular speed formula will not work unless the angle A is in radians. Okay. That's not completely true. We could have, we could say how many degrees is happening in a unit of time, but usually we don't. Okay. Usually it's going to be radians that we're dealing with. Okay. So example, the blade on a shop fan rotates 8.0 revolutions per second. Calculate its average angular speed in radians per second, round to the nearest whole number. Okay. So we have 8.0 revolutions in 1 second. Now this is really just like a conversion kind of problem. Okay. Now we know that 1 revolution is equal to 360 degrees. And we know that 360 degrees is equal to 2 pi radians, or how about I say it this way? So 360 degrees is 1 revolution. So that's going to get rid of revolutions and give me degrees. But then I know that, I know that, let me back up. Oh, I didn't bring my white out. Oh, well, I know that there are pi radians in 180 degrees. Does that make sense? So this is going to give me radians per second because degrees will cancel. Okay. Now 180 degrees will cancel with 360 degrees, leaving 2. So really all I have is 8 times 2 times pi. So 8 times 2 times 3.14159. And so that is 50.26, blah, blah, blah. But my directions say round to the nearest whole number. Okay. So if I round 50.265, blah, 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 that's going to be approximately 50 radians per second. You follow me on that? Now, another thing to remember, and I'm going to write this down for your convenience. 1 revolution is equal to 2 pi radians. So if you will remember that 1 revolution is 2 pi radians, that will allow you to calculate this without having to use the degrees. Does that make sense? So if I would have known that fact, right, I could have said, well, I've got 8.0 revolutions per 1 second. So that would be times 2 pi radians over 1 revolution. And that would get rid of revolutions. And I would just be taking 8 times 2 pi, which is really what I ended up doing anyway, because the 180 and the 360 cancel, leaving 2. You with me? So that's still going to give me about 50 radians per second. Piece of cake? Example 8. A belt-driven drum of radius 28.4 centimeters makes 1 revolution every 0.250 seconds. What is the linear speed of the belt driving the drum in centimeters per second? Round to the nearest whole number. Okay. So what we know in this problem is we know revolutions. We know that 1 revolution is happening every 1/4 of a second, every 0.25 seconds. Okay. Now it's telling us that the radius of this drum is 28.4 centimeters. Okay. So if you visualize that, so 28.4 centimeters is the radius. Okay. And this thing is making 1 revolution every 0.250 seconds. So in other words, if you think about that, 1 revolution every 1/4 of a second means it's making 4 revolutions every second. So that thing's spinning around 4 times every second. Does that make sense? Okay. So our question is, what's the linear speed? Okay. So if you were like sitting here on the edge of this drum, how fast would you be spinning around? Okay. But we want it in like centimeters per second, or yeah, in centimeters per second, as opposed to, revolutions per second. Okay. Does that make sense? So how are we going to do that? Well, what we need to do is think about what the distance is. Okay. So the distance that thing travels every time it makes a revolution is going to be the circumference of the circle. So it's going to travel the circumference of the circle every time it makes a revolution. Okay. So the circumference of the circle is going to be 2 times pi times the radius, which is 28.4 centimeters. So 2 times 3.14159 times 28.4. So that is 178.442312 centimeters. And I'm going to carry that decimal out for right now. 178.442312 centimeters. And that's, again, the significance of that is that's how far it's traveling linearly every time it makes a revolution. Does that make sense? Okay. So if we're traveling 178.442312 centimeters, 442312 centimeters for each revolution, okay? And we know that it's making 1 revolution per second. So that's in 1 revolution. So if I multiply that by 1 revolution for every 0.25 seconds, revolutions are going to cancel. And if I do this calculation, I'm going to be left with centimeters per second. So if I pull that in, and I'm just going to say take that divided by 0.25, and technically it was 0.250. So that's going to be 713.769. 248 centimeters per second. And if I round to the whole number like I'm directed, so that's about 714 centimeters per second. So again, it's really kind of just, you got to think your way through it. What does it mean when you make 1 revolution? Well, you're traveling the circumference distance. So figure out the circumference. So you're traveling the circumference every revolution, and then just convert. Okay, 1 revolution every 0.25 seconds. So 714 centimeters a second. Okay. Okay, so that primarily what we've talked about so far, right? We've talked about degrees, minutes, and seconds, and we've talked about radians, and then we talked about, okay, why would we use a radian? And that's where the length of a arc or the area of a sector came in, right? That kind of thing. Okay. Well, for the rest of this section, we're going to focus on right triangles. Some of this stuff we've already learned before, some of it not, okay? And which again is what trigonometry is really about. Trig is about triangles, okay? And how triangles work. And specifically, a lot of trig is not just about triangles. A lot of trig is about right triangles. So what's a right triangle? If you'll remember, a right triangle has a 90-degree angle in it, okay? Now, so we had talked a little bit about right triangles back in the geometry chapter, back in chapter 8, okay? So there's a couple of things we know about triangles. One, the 3 angles in a triangle have to add up to be 180 degrees. So if I've got a right triangle, then one of those angles is 90 degrees, which means the other 2 angles has to add up to be the other 90 degrees in order to get to 180 degrees. So like if I told you that this angle right here was 20 degrees, then that would mean this angle would have to be 70 degrees, so that when you add 20 and 70 and 90, it would be 180. Okay, does that make sense? Okay. So a right triangle is one that contains a right angle, a 90-degree angle. All of the triangles shown below are right triangles. In each triangle, the right angle is marked, and we always mark the right angle with this square, okay? So all of those are right angles, right? And so right triangles. A right triangle is said to be in standard position if one leg is horizontal, the other leg is vertical, and the right angle is on the opposite side. Which of the triangles above are in standard position? Okay. So if you look at like this triangle, what was our rules? One leg's horizontal, the other's vertical, and the right angle is on the right side. So we have this leg is horizontal, this leg is vertical, but the right angle is on the left side. So that's not considered standard position. So this is not standard position, okay? One leg is vertical, one leg is horizontal. The right angle's on the left side. So this is not in standard position, okay? This is not in standard position because the one leg and the other leg's not vertical and horizontal, okay? This one is in standard position. This is horizontal, this is vertical, and the right angle's on the right side. So this is, yes, this angle's in standard position. This one's not. Make sense? Okay. So it's easiest to look at right triangles when we have them in standard position, at least for trigonometry's purposes. Okay. So we like to have them in this standard position for the sake of trigonometry. Okay. If a triangle is not in standard position, remember that the legs and the two sides forming, remember that the legs are the two sides forming the right angle, and the hypotenuse is the side opposite the right angle. The hypotenuse is always the longest side in a right triangle. So like if you look at this triangle right here, here's the 90-degree angle, the side opposite that is the hypotenuse. So that means this and this are the legs. Okay, does that make sense? So if a triangle's not in standard position, we could rotate it and put it in standard position. Okay. So looking at our picture here, here's the right angle. So opposite of that is the hypotenuse. Here's my horizontal leg, here's my vertical leg. Okay. Now, we've also already learned the Pythagorean theorem in this class. So recall from section 8.3 that the Pythagorean theorem is an equation relating the lengths of the sides of any right triangle. This formula is true for every right triangle. So if I have a right triangle, and if A and B are the legs, and if C is the hypotenuse, then if I take A squared plus B squared, that will equal C squared. Okay, so we say the sum of the squares of the two of the two legs will equal the square of the hypotenuse of a right triangle. Okay. Note, in the formula, the letters A and B representing the legs are interchangeable, but C must always represent the hypotenuse. Okay. So C is representing the hypotenuse. It doesn't really matter if you call this A and this B, or if you call this A and this B. You can swap those around, it doesn't matter, but C has to be the hypotenuse. In other words, it's the hypotenuse squared by itself, and the leg squared added up is the other side. Okay. So example 9, find the missing side in each right triangle shown. Round to the nearest tenth if necessary. Okay. So in this triangle here, I have the two legs that are given. It's the hypotenuse that I need to find. Okay. So I know that 20 squared plus 21 squared equals C squared. Now 20 squared is 400, 21 squared is 441. And if I add 400 plus 441, that's 841. So 841 is equal to C squared, which means C is going to be the square root of 841. And if I find the square root of 841, that's 29. And that works out perfectly. Okay. So the length of C is 29, I should say, inches. And I know this is inches because the legs were given in inches. Piece of cake. Now I picked this problem for the example because the square root of 841 works out really nice and neat. That's not typically going to happen, right? Usually we'll end up with something that we'll have to round. Okay. What makes B different from A? In B, look at what's opposite the right angle, 18.1. So that's the hypotenuse that I know. And I know one of the two sides. So if I call this side A, then I would be looking for side B. Does that make sense? Okay. So 6.5 squared plus B squared equals 18.1 squared. Okay. So I got to solve this one. 6.5 squared is 42.25. 18.1 squared is 327.61. If I take 327.61 minus the 42.25, I get B squared is equal to 285.36, which means that B is the square root of 285.36. And that would be approximately 16.9 if I round to the nearest tenth as directed. Okay. So side B is going to be 16.9 centimeters long, approximately. So there's really not anything new there. We did that back in chapter 8 when we used the Pythagorean theorem. Okay. Now, there are some special right triangles that if you will remember and recognize them, you will not have to use Pythagorean theorem. Okay, does that make sense? So now it doesn't work in general, but it works for some special right triangles. Okay, so that I'll be able to figure out what the side length is of a right triangle or what the hypotenuse is of a right triangle without having to go through the trouble of Pythagorean theorem. If you don't remember it, you can always go back and use the Pythagorean theorem if you want to. Okay. So three very special right triangles are used often in practical work. They are the 45-45-90 triangle. So like this is the 45-45-90 triangle, meaning that we got a right triangle and then the other two angles are both 45 degrees, which makes it an isosceles triangle. Okay. So if this is 45 and this is 45, then this side and this side have to be the same length. Okay, does that make sense? If these lengths are 1, then the hypotenuse will be the square root of 2. 1 square plus 1 square would be 2. And so square rooting, that would be the square root of 2. So if we have a 45-45-90 degree triangle, the side lengths are in the ratio of 1, 1, square root of 2. Does that make sense? So the two legs will be like 1 to 1, and then the hypotenuse would be whatever the leg length is times the square root of 2. Okay. The next is the 30 degree, 60 degree, 90 degree triangle. Okay. So this is an example of the 30 degree, 60 degree, 90 degree triangle. So again, in this case, 90 degrees is going to be here. And so the ratio that's going to always happen is if you look at the side opposite of the 30 degree angle, whatever that side is, the hypotenuse will be double it. Okay, so like if this is 5, the hypotenuse would be 10. Okay, the side here opposite of the 60-degree angle will be this times the square root of 3. Okay, so it's always going to be in that ratio. And then the last one is the 3, 4, 5 triangle. So in the 3, 4, 5 triangle, so like this side is 3, this side is 4, the hypotenuse is 5. So again, notice that it's 45 degree, 45 degree, 90 degree triangle. That was this one. 30 degree, 60 degree, 90 degree triangle. That's this one. But the 3, 4, 5 is not the angles. It is the sides, 3, 4, 5. Does that make sense? So if we have a triangle in that ratio, it is a right triangle. Okay. So whatever, again, like whatever this is, it'll be like 3 compared to whatever this is, it'll be 4, this will be 5. So in other words, what I'm getting at is like if this was 6, so that it's 2 times 3, then this would have to be 8 so that it's 2 times 4, and this would have to be 10 so that it's 2 times 5. They got to be in the 3, 4, 5 ratio. Okay, does that make sense? Now the angles are about 53 degrees opposite of the 4 side and 37 degrees opposite of the 3 side. And that's not exact, but it'll be approximately a 53 degree, 37 degree, 90 degree triangle. Okay. So again, what am I getting at? For a 45, 45, 90 degree triangle, the 2 legs, the shorter sides are the same length, and the hypotenuse, the longer side, is the square root of 2. And this is sometimes referred to as an isosceles right triangle. Okay, because again, that's gonna always be the same length right there. Okay, so for any 45 degree, 45 degree, 90 degree triangle, when given the length of a leg, multiply by the square root of 2 to find the length of the hypotenuse. When given the length of the hypotenuse, divide by the square root of 2 to find the length of each leg. Okay, does that make sense? Okay. So consider the triangle XYZ shown to the right. If XY is 6.8 centimeters, I should say, find Y, or find YZ and find XZ, if I could read, round to the nearest tenth. Okay. If XZ is 16.1 inches, find XY and YZ. Okay. So again, this is a 45 degree and this is 90 degrees, which means this has to be 45 degrees. So this is a 45, 45, 90 degree triangle like this. Okay. So if XY is 6.8 centimeters, that's this side, then what would YZ be and what would XZ be? Okay. So YZ is a leg just like XZ is. So YZ is going to be the same length as XZ because this has to be an isosceles right triangle. Does that make sense? Okay. XZ is going to equal the 6.8 centimeters times the square root of 2 because the sides are in the ratio of 1, 1 square root of 2. Okay. So 6.8 times the square root of 2 is about 9.6. And our directions say round to the nearest tenth. So 9.6 centimeters. Is that hard? Okay. If XZ, so that's this, now this isn't 6.8 anymore, new problem. if XZ is 16.1 inches, find XY and YZ. Well, that's the hypotenuse. So if I divide the hypotenuse by the square root of 2 in this 45, 45, 90 degree triangle, that's going to give me the XY and the YZ both. Okay. So XY is going to equal 16.1 inches divided by the square root of 2. So that is 11.4 if I round to the nearest 10. And it'll be inches. Okay with that? And so that means YZ is equal to the same thing. Not too terrible. So again, the key here is to figure it out. You can use the fact that 45 degree, like the 45, 45, 90 degree triangles always work that way. Okay. The two sides or the two legs are the same length, and then the hypotenuse is the square root of 2 times that length. Okay, does that make sense? Excuse me. Now, if you were to forget that, if I told you like this side 6.8, then it's obviously our isosceles triangle. So if this is 6.8, this is 6.8, you could also figure out what that had to be by using the Pythagorean theorem. So 6.8 squared plus 6.8 squared and then square root it, that's also going to give you the 9.6. And I'll just show you that. If I take 6.8 squared plus 6.8 squared, that's that. And if I take the square root of 92.48, I get the 9.6. Okay, does that make sense? Likewise, if you know this is 16.1, well, then this would be, say, like x and x, they're the same thing. So x squared plus x squared would equal 16.1 squared. Well, 16.1 squared would be 259.21. So on the left side, I have 2x squared, and that equals 259.21. So I'd have to divide by 2. So x squared equals 129.605. And if I square root the 129.605, that gives me the 11.4 that we got. Okay. So you could use the Pythagorean theorem if you want, or if you remember the ratios, makes it easier. Okay. For a 30 degree, 60 degree, 90 degree triangle, the length of the side opposite the 30 degree angle, the shorter leg, is exactly 1/2 the length of the hypotenuse. The length of the side opposite the 60 degree angle, the longer leg, is the square root of 3 times the length of the shorter leg. So for any 30 degree, 60 degree, 90 degree triangle, when given the length of the shorter leg, which is again opposite the 30 degree angle, multiply it by 2 to get the length of the hypotenuse, and multiply it by the square root of 3 to get the length of the longer leg, which is the one opposite the 60 degree angle. When given the length of the hypotenuse, divide it by 2 to get the length of the shorter leg. Then multiply this result by the square root of 3 to get the length of the longer leg. So if you know the hypotenuse, divide by 2 to get the shorter leg, then take the shorter leg times the square root of 3 to get the longer leg. When given the length of the longer leg, divide it by the square root of 3 to get the length of the shorter leg. Then multiply this result by 2 to get the length of the hypotenuse. So if you're given the shorter leg, you can find the hypotenuse and the longer leg pretty much directly, okay? If you're given the hypotenuse, find the shorter leg and then use the shorter leg to find the longer leg. If you're given the longer leg, find the shorter leg and then use the shorter leg to find the hypotenuse. So the key is to find the shorter leg, okay? So example 11, consider the triangle ABC shown to the right, okay? If A is 5 feet, find B and C, round to the nearest tenth. If C is 8 inches, find A and B, round to the nearest tenth. If B is 15 centimeters, find A and C, round to the nearest tenth, okay? So in part A, we're told that A is 5 feet, and we're supposed to find B and C. Okay. Well, again, this is a 30-degree, 60-degree, 90-degree triangle. So we have this situation. And so we can use, well, so we can use what we just said right here. Okay. So I know the shorter leg. If I want to find the hypotenuse, C, it's going to be double the shorter leg. So C is going to equal 2 times A. So that's 2 times 5 feet, which is 10 feet. So this, if this is 5 feet here, this has to be 10 feet. Okay. To find B, B is going to equal A times the square root of 3. So in this case, that's going to be 5 feet times the square root of 3. Does that make sense? So 5 times the square root of 3 is about 8.7 if I round to the tenths as I was directed. Any questions about that? Pretty straightforward. If C is 8 inches, find A and B. So now that's gone, that's gone. If this is 8 inches, what's A and B? So in this case, I'm given the hypotenuse. So the key, remember, is to now find the short side. Once I know the short side, then I can find the longer leg, okay? So A is going to equal half of C. So C divided by 2. So in this case, that's going to be 8 inches divided by 2, which is 4 inches. And now once I know that, B is equal to A times the square root of 3. So that's going to be 4 inches times the square root of 3. So that's going to be about 6.9 inches if I round to the tenths as directed. Make sense? C, if B equals 15 centimeters, find A and C. So now I don't know this one. I know this is 15 centimeters. So I need to find A and C. So in this case, I'm given the longer leg. I need to find the shorter leg and the hypotenuse. And the key again is to find the shorter leg, because the hypotenuse will be double the shorter leg, okay? So to find A is going to equal B divided by the square root of 3. So in this case, that's 15 centimeters divided by the square root of 3. So that's going to be about 8.7. So 15 centimeters, this would be 8.7 centimeters. And so now C is 2 times A. So that's going to be 2 times 8.7 centimeters. And 2 times 8.7 is 17.4. Make sense? I do want to point out, had I done like 2.8, 2 times 8.660254038. In other words, if I hadn't rounded, then I would get 17.3 instead of 17.4. You with me? So I would have a little bit of a discrepancy there from rounding if I don't round like that. Does that make sense? My math lab should take either answer, so it shouldn't be a problem, but you could possibly get, again, a little bit of discrepancy there. Okay. Okay, so we got one more thing to talk about, a couple of applications, and then we'll call it a day. Okay. So a 3, 4, 5 triangle is a right triangle. So anytime we have a triangle in the ratio of 3, 4, 5, it's going to be a right triangle. Okay. So in the same way, if you have like, now again, the 3 is like the short leg, the B is the longer leg, and the 5 is the hypotenuse. So if like the shorter leg and the hypotenuse are in a ratio of like 3 to 5, then you're going to be able to figure out what the longer leg is. It's going to be in the ratio of like 3 to 4 or 4 to 5. Does that make sense? Okay. So basically, if you know any of the two sides, you can find the third side by recognizing that they're in a 3, 4, 5 ratio. Okay. Does that make sense? Now, again, you could always also use the Pythagorean theorem. And we could have used the Pythagorean theorem on this if we didn't recognize the 30, 60, 90, for example. Okay. The angle opposite the side 3 units long is approximately 37 degrees, and the angle opposite the side 4 units long is approximately 53 degrees. If the side lengths of a triangle are proportional to the numbers 3, 4, 5, then they will also create a right triangle with the same angles. Okay. So for the triangle shown, find the length of side A. Now, if you looked at this triangle and you're like, gosh, I've got no clue, then you could use the Pythagorean theorem to find it. So you could take like 20 square minus 12 squared and then square root in order to get A. Okay. But if you recognize that like 12 is 4 times 3, and if you recognize that 20 is 4 times 5, so that this is a 3, 5 ratio, then that tells me that A is going to be 4 times 4. Okay, so that I've got the 3, 4, 5 ratio, but it's 4 times 3, 4 times 4, 4 times 5. Does that make sense? So A is going to equal 4 times 4 meters. So that's going to be 16 meters long. I almost wrote square meters, but it's not square meters, it's just meters. Now, if you were asked, and we weren't, but if you were asked, like, what's this angle right here? That angle right there would be about 37 degrees. And if you were asked, what's this angle right here? That angle is about 53 degrees. And I know that because it's a 3, 4, 5 ratio, and that always works that way. Make sense? Again, if you didn't recognize the 3, 4, 5, you could still figure out the 16, because if you took 20 squared that's 400. If you took 12 squared, that's 16. And if you take 400 minus 144, I think I just said that's 16. That's 144. You get 256. And if you square root the 256, that's 16. Okay, makes sense? So you've got multiple options of figuring out a problem. So practical applications, parallel pipes. Parallel pipes are connected by 45-degree fittings as shown. What is the length of the connecting pipe from A to B round to the nearest 10th? So this would be maybe like something you would have to figure out if you're a plumber, right? So you got a pipe here and you got a pipe here, and those pipes are parallel. And the significance of them being parallel is from what we learned back in chapter 8 about when you have two parallel lines cut by transversal, you can figure out like the alternate interior angles are the same and all that stuff, okay? Well, mainly if this is a 45-degree angle right here, this is a 90-degree angle, then this has to be a 45-degree angle, okay? And so we have a 45-degree, 90 triangle, okay? Does that make sense? So now we're told here that there is an offset of 8.5 inches. So this pipe down here is 8.5 inches below this pipe right here. Does that make sense? Okay. So in other words, that's the length of the side of that triangle. Okay. Which means this right here is also 8.5 inches because it's going to be isosceles because of the 45-degree angles. Okay. Does that make sense? So if I want to find the length L, the length of this pipe right here, okay, then I can figure that out either because this is a right triangle, I could use Pythagorean theorem, or I can recognize that this is a 45, 90-degree triangle and use the fact that the length will be whatever the leg length is times the square root of 2, okay? So L is going to equal 8.5 inches, the length of the legs, times the square root of 2. Well, 8.5 times the square root of 2 is 12.0 if I round to the tenths like I'm directed, okay? So that piece of pipe is going to be about 12.0 inches long. Now, again, just for the sake of saying it, if I didn't recognize the 45-degree rule, the 45, 90, if I take 8.5 squared, and if I take 8.5 squared again, if I add those two things together, 72.25 plus 72.25, that would be what L square equals. So if I take the square root of 144.5, that also gives me the 12.0. Okay. Any questions? Last example. The steel gusset shown in the figure is made in the shape of a right triangle. The gusset is to be welded in place along all three sides. What will be the total length of the weld? Okay, so this is a gusset. It's going to be like welded in the corner, right? Or really it's on all three sides for support. Okay, does that make sense? So we're going to weld along this side. We're going to weld along this side. We're going to weld along this side. And the question is, what's the total length of the weld? In other words, we need to know the perimeter of the triangle. Okay. Well, I know 15 and 20, so I'm going to need to know what's the hypotenuse. Okay. And then once I know that, I'm just going to add the 3 up. Okay. Well, we could figure that out using the Pythagorean theorem, or we could recognize that 15 right here is 5 times 3. We could recognize that 20 right here is 5 times 4. So the two legs are in the ratio of 3 to 4. Does that make sense? So the hypotenuse has to be 5 times 5 so that it's a 3, 4, 5 ratio. Okay. So in other words, that's going to be 25 inches. Okay. Now again, if you didn't remember that, you could take 20 squared, that's 400, 15 squared, that's 225, and 400 plus 225 is 625. And if I square root 625, that's 25. Okay, so I'm doing it by the special triangles, but I could have also done it with Pythagorean theorem. Okay, so my weld is going to be the perimeter. So 15 inches plus 20 inches plus 25 inches is going to be 60 inches. Is that okay? So we had weld, and altogether we've welded a length of 60 inches. So that finishes section 10.1. So you should be able to handle the section 10.1 homework. Okay. So next time, we'll look at section 10.2. Okay. In section 10.2, we're going to be talking about what are called the trigonometric ratios. So we're going to talk about, you may have heard them before, sine, cosine, tangent. Okay. So, so we'll be looking at sine, cosine, tangent ratios, and we'll be applying those to figure out things about right triangles. Okay. That will finish us for the semester. Okay. So it'll probably take us, I don't think it'll take us the full time on Wednesday to get through this, but if it does, it does. Okay, so that's sort of the plan. We finish everything on Wednesday. Then we'll talk a little bit about the test after we finish this. Next Monday, again, my plan is that that's just going to be kind of a free day. So it's like a study time. So you won't have to come to class next Monday unless you just have questions. If you have questions, then come to class and you can ask those. I'll probably not even be in the classroom myself. I'll come to my office. Okay. So I'll be in my office, and if you have questions, you can come to my office. If all of you come, then maybe we'll come down to the classroom and I'll answer your questions. Okay. If just one of you comes, we'll stay at my office and I'll answer your questions there. If you don't have any questions, you don't have to come. Okay. Then Wednesday, you'll take the last test, and that'll cover chapters 8, 9, and 10, which is on the geometry stuff in chapter 8. The 9 was the prisms, so that was like the volumes and surface area and so on. And then 10 is the triangle stuff, trigonometry. Okay. See you on Wednesday.